Okay, so now we've finished up linear regression, and we're going to talk about something a little bit different called logistic regression. And so far, we've actually covered a large part of our book. We've covered large parts of chapters 2 through 8 in the book. And the bit about logistic regression in the book is really just in one section that I've scanned and put on Moodle, section 9.6 of the textbook. And eventually I'm going to ask you to read that. So I'm not going to read through all the objectives here, but I will just mention that we're going to talk about simple logistic regression, which, just like with linear regression, that means one x variable. And we'll also talk about multiple logistic regression, which is more than one x. So I'm hoping that as we move through this, you'll see there's a lot of similarities between the setup for linear and logistic regression, especially on the right-hand side of the model in terms of the x's and the betas. For the left-hand side of the model is going to be a little bit different, because now we're going to talk about modeling probability or odds rather than expected values. And we'll also talk about many of the same things for logistic regression that we talked about with linear regression, different assumptions and making inferences and so forth. So let's first talk about some terminology that you might hear. If you remember proc GLM, which is one of the procs that we were using for linear regression, GLM stands for General Linear Model. And that's a name for models that is really conventional linear regression that we've been talking about all this semester, where we have a continuous response variable, a continuous y, and we can have continuous or categorical predictor variables. And as you saw, it includes multiple linear regression, which is what we've been talking about. ANOVA. In chapter 4C, we did one example that was really ANOVA, which you've talked about in Stats 212. Something called ANCOVA, analysis of covariance, which you'll cover more in Stats 325. And we saw a little bit of ANCOVA, even though I didn't call it that. The models where, for instance, where we were fitting interaction terms with sex by mom's height, for instance, or sex by dad's height, to model your current height. Those class activities 5 and 6 were really using a form of ANCOVA, analysis of covariance, but I didn't call it that then. So what we're going to move in now, so that was the general linear model. We're going to move into something now called the generalized linear model. As if statisticians could be more confusing. We have something called the general linear model, which is really just our linear regression models. And we're going to move into the generalized linear model, which is a larger class of models, where a general linear model is actually a special case of a generalized linear model. And the response variable now might be categorical rather than continuous. And some of you have categorical variables for your projects, so this will be very useful for you. The response variable y has a mean mu, which is assumed to be some often non-linear function of the beta x terms. So we still have the beta x terms, they're still present in our model, but now our response variable is going to look a little different. So generalized linear models extend what you've already learned regarding linear regression to cases where we just might not have the normality assumptions. So linear regression is actually a special case of a generalized linear model. So general linear models are a special case of generalized linear models. As I said, statisticians like to be a little bit confusing. Logistic regression is also a special case of a generalized linear model. So let's break down the parts of a generalized linear model. There are really 3 parts of any generalized linear model. The first is the linear predictor or systematic component. And that's the beta x's. beta 0 plus beta 1 x1 plus beta 2 x2 all the way out to beta k xk. This is really very similar to multiple linear regression. Okay. And of course you saw that simple linear regression is really just a special case of multiple linear regression, where we just have one x. So the linear predictor is actually composed of all predictor and explanatory variables of interest, both quantitative and categorical, or qualitative, if you prefer, qualitative. As well as variables that represent higher order terms. So it's exactly the same type of idea that we were looking at in multiple linear regression. We might have, and they're all multiplied by their model coefficients, slopes, and betas. But the next part of a generalized linear model is called the link function, which is a function which I call g of mu, which is a function of the mean. So when a response is continuous, the link is usually the identity function. And what I mean by that, you saw this already. So here's a simple linear regression model. Remember, we were modeling mu, which is the same as the expected value of y, x1, for simple linear regression. So the function of mu that we're modeling is just mu itself. So that's why we say that's the identity function. But when we have discrete or qualitative data for the response, we must transform the response variable to fit to the linear predictors. And that transformation we're going to call a link function. The link function maps the mean of our response variable onto the real number line from minus infinity, that's negative infinity, to positive infinity. Positive infinity. So as you'll see, and I'll show you how this works for a binary response variable down below, but the link function, we know that a linear function always goes from negative infinity to positive infinity. For continuous variables, that's not a problem. But when we have discrete counts or binary data, for instance, then they don't map easily from negative infinity to positive infinity. So the purpose of the link function is to expand the range of our response variable. Then there's also a random component. If we use least squares linear models, the random component epsilon, so remember epsilon from our linear models, requires normality and constant or equal variance of residuals, in addition to independence. So with linear regression, we had these assumptions, the line assumptions. That was for the least squares modeling that we did. But now we're actually going to use a new method called maximum likelihood, which we'll talk about in future notes, to estimate the parameters of a generalized linear model, which requires simply assuming that the observations are independent random samples from some specified distribution. We have to specify the distribution of our random terms, but it might not be normal. Okay. See if I can get this in better focus for you. Okay. So I said simple linear regression is a special case of a generalized linear model. Why is that? So here's your simple linear regression again. yi equals beta 0 plus beta 1 xi plus epsilon I. And remember that I here just stands for each observation. So if you're, hopefully by now you're getting used to this I index. I don't use it all the time, but that just means each independent observation. The systematic component again, the linear predictor part is whatever is a beta or is an X attached to a beta. So the systematic component here is the explanatory variable. Remember, it can be continuous or discrete or categorical. The systematic component is linear in the parameters. We also have a link function. The link function here is just the identity function again, because we're actually modeling our function of mu is just mu. We're modeling the mean directly. So this is actually the simplest link function. Yeah. Again, we're just modeling expected value of y equals mu equals beta 0 plus beta 1 xi. Okay. Then we have a random component. The response variable here, we assume that the response variable, and we generally assume that the errors are independently normally distributed with mean 0 and variance sigma squared. So remember, we wrote that as epsilon squiggle n 0 sigma squared. Remember that the epsilons here are the error terms, the random errors, which we generally don't get to see. The squiggle are distributed as, and I'll usually put a little IND above up here to indicate independently, because that's pretty key here. This means normal with mean equals 0 and variance equal sigma squared. So this is just a review, right? But this shows that simple linear regression is just a special case of generalized linear models because we have all three parts. We have the linear predictor, the x's and the betas. We have the link function, which in this case is just mu. And we have the random component, the epsilons, which we specify our distributional assumptions about. So what is this link function? There are different types of models that you might fit that are generalized linear models. And depending on the type of response function, the link function can actually take on different forms. We're actually just going to look at two in this class. We're going to look at the most common link functions for continuous or binary. That's what we're moving into now. But there's so many different types of link functions. Some models that we've already looked at that are special cases here, linear regression. Remember that we assume that the errors are normally distributed. The link function is identity. We're directly modeling the mu's. And the x's and the betas, the x's can be categorical or continuous, and we multiply them directly times betas. Again, ANOVA is also a special case of this, and this you've seen already in Stats 212. And ANOVA, we typically just have categorical predictors, as you saw in the chapter 4C notes. ANCOVA, you'll get to in Stats 325 in Design and Analysis of Experiments. This stands for Analysis of Covariance. And we saw a little bit of that here in this class. I didn't call it Analysis of Covariance, but that's what we were looking at in Activities 5 and 6 was really an ANCOVA model. And logistic regression is what we're going to start talking about now, where the random part is going to follow what we call a binomial distribution, and the link function is what we're going to call the logit. I'll talk more about that down below. But again, just like for linear regression, we have continuous or categorical predictors. So what do I mean by binary y variables? Logistic regression is a generalized linear model where our y variable is binary. And you can think of that as 0 or 1. So it takes on the values 0 or 1. It's sort of like a dummy variable, but for the y. Okay. So as an example, here's some interesting data for you. In the mid-1800s, this is before the Civil War, in the winter of 1846 to 47, about 90 American pioneers in a wagon train, which was called the Donner Party, or the Donner-Reed Party, were traveling from Illinois to California. And they were unable to cross the Sierra Nevada mountains of California before the winter, so they got trapped. And there's some really good documentaries and movies about this. Almost half of them starved to death, so it's a little morbid. But anthropologists have examined the data to study the theory that females were better able to withstand the harsh conditions than males. So I'm going to introduce a new term here that we haven't talked about very much. I might have mentioned it in passing. But it's a very important term in statistics, and that is observational units. Observational units are the smallest unit in your data on which we have observations. And for most of the data sets that we have looked at in this class, that would be, and in this case, it would be individual people or individual animals, say. So we're going to have, if you look at the data, they're actually on Moodle, and we're going to use them later on. But the observational units in this study are individual people. And the response variable is whether they survived or died. And it's binary. It can only take on two values. Okay. Which variables might help explain why some people survived and some did not? So which might help us predict whether or not someone was going to survive? So what do you think? So I mentioned up above, they're looking at sex. So the sex of the individual might predict whether somebody survived or died. But what else do you think? What always predicts survival? Age. So age might help predict survival. Here we're talking about individuals potentially starving to death over a period of time. So what can help prevent somebody from starving to death? Maybe something like percent body fat. What about if they're already sick, say? So maybe the general health status. What else might help somebody survive? Maybe if they have other people caring for them or helping them out. So if they have family members around. Some of these things you'll see make it into the data set, whereas other things do not make it into the data set. We don't have information on all of these things. We certainly don't have information on body fat. But with logistic regression models, we'll consider situations where there's a binary response. So, for instance, yes or no, success or failure, 0-1 situation. You also might have win, lose if you're modeling sports data, for instance. I know I have a couple project groups who maybe are modeling wins and losses in sports data. You also might model something like employed, unemployed. Right? If you're modeling college acceptance data, you might have accepted, rejected. Okay, these are all binary variables that you might model using logistic regression. Another one is if you're modeling, say, a new treatment for a certain disease, you might have successful treatment versus unsuccessful treatment, or cured versus not cured is another way to think of that.